Well, good day, everyone. I am Tanalikhit from the Department of Physics at KAIST. Today, we will discuss the Landau Pole, which is also known as the zero charge problem or the Landau duality, or you may call it Moscow pole or Landau ghost, as you wish. Interestingly, this is a key issue in the quantum electrodynamics or QED. Well, we can get started and you'll see how it is a problem of the QED. So the first question is, what is the Landau pole? The Landau pole or the zero charge problem is a key issue in QED, as I mentioned. This thing describes how the effective charge represented by the landing cupping constant decrease as we move to very short distances or very high energies. It cannot be considered as the complete theory. This is a key equation of the Landau pole. So you can see that as the reference scale or R naught goes to zero, here the effective charge will go to zero too. So it shows no meaningful interaction and it less some key motivation for us because it want to have the fundamental understanding about it, like how does this result reflect the nature of the quantum interactions. And it also suggests the need for the new theories because QED is incomplete. So we need something to replace it. So it's also relevant to the modern physics, like it will lead to the more advanced theory like QCD, quantum chromodynamics. Now here are some topics that I'm going to cover today. I will talk about some introduction and then some history and the physics behind it. I will mainly talk about the work by Landau, Abikosov, and Karanikov, and Landau and Pomeranchuk. Then I will talk about the Landau pole in the context of particle physics, mainly about the QCD. And then I will show you the impacts of it on physics in general and the physics as a community of the physicists. Now let's talk about the field theory. What is it? Like why the field theory is necessary? Well, I will answer it the same way as Vladimir Beretetsky answer is in one of his articles. He said that field theory is quite essential for understanding interactions in the physical world because you know every interaction, whether electromagnetic, gravitational, or otherwise, it has to propagate at a finite speed. So to describe it, we need some medium, and that medium is a field, and it will carry the interaction across space. We know that the fields are not static, like they are dynamic system, and then they have the infinite degree of freedom. It means that they can describe enormous range of physical phenomena. Additionally, in relativistic system, particles are not fixed entities, so it can be created or annihilated, destroyed naturally in such systems. So this cannot be explained using the simple mechanical models. It requires the field theoretic framework that provide the consistent description in the processes. Let's talk about some early challenge in the electrodynamics. The major challenge are due to the divergence in both the classical electrodynamics and QED, quantum electrodynamics. In the classical electrodynamics, there is the cell energy problem. It shows some singularity, as you can see, is inverse of R, and as R go to zero, then kaboom is go to infinity. But as we invent the QED, we can see that for the low order approximation, this is okay. It successfully addressed the previous problem. However, for the higher order corrections, we face the new divergence, like is diverged logarithmically as we determine this integral. The topics of renormalization. Well, the renormalization in QED will resolve the divergence by redefining physical parameters such as charge or mass. And this cartoon, I brought it from Nambu book, like Nambu in Nambu Koto. It showed the renormalization process, like it will sweep away the infinity, like tidying up the messy room. You can see that we do the same thing as renormalization. It seems like some, how to say, mathematical trick that, well, people will question it repeatedly. However, it ensures some agreement with the experiment, like for the lamp shift, as shown here, that for the if we include some radiative correction, it will explain the energy level shift in the hydrogen and accurately predict the energy difference between S1 half and P1 half states. And still, the renormalization will leave the conceptual issue unresolved because it works mathematically, as I mentioned, but the infinities that are simply absorbed is not fully explained. We do not understand it physically, but it's worked well mathematically. So now let's see some timeline. This timeline will summarize the key milestone in the theory of electrodynamics and the quantum field theory, which later lead to the Landau pole. Well, it's all begin by the James Clerk Maxwell, who formulated the first field theory, the classical electrodynamics. Then in early 20th century, J.J. Thomson and Hendrik Lorentz realized the divergence problem in electromagnetic mass, and not so long, the foundations of the quantum electrodynamics or QED just emerged in between 1928 to 1930 by the contribution of Paul Dirac, Werner Heisenberg, and Wolfgang Pauli. Then between 1947 to 49, we have Richard Feynman, Julian Schwinger, Shinichiro Tomonaga, who developed the idea of renormalization and then is later unified. Freeman Dyson was the one who unified the concept developed by those three people. Then in 1954 to 1955, Landau, Abikosov-Karanikov, and Landau and Pomeranchuk derived the running of the charge and is revealed the Landau pole. So we can see that the effective charge vanishes at the short distances. And this continue to, well, we have still in the same year, Yang and Mill developed their Yang-Mill theory. And then in the 1964, Murray Gell-Mann developed the idea of the QCD, quantum chromodynamics. Finally, David Gross, Frank Wilczek, and then Poischer, they study and discover asymptotic freedom in QCD too, and they also solve the Landau pole problem in the strong interaction. Well, that's all the history. So now here come to the seminal papers by Landau, Abikosov, and Kerensky in 1954. The problem that they deal with address with the divergence in the quantum electrodynamic of QED. So they see that this problem is caused by the point charge, and they solve this by investigate the effect of introducing the finite charge size or R0. Well, their key contributions was to introduce the regularization by cutting off the integral at R0 and then applying the perturbative solution to study the landing of the charge with the scale. And the significance of their work is quite profound, as I would say that it pioneered the understanding of scale dependence of the QED and set the stage for the zero charge theorem. You can see that the finite result could be achieved using the regularization technique, and this is the turning point of the QED. Now, the subsequent paper by Landau and Pomeranchuk, they explicitly derive the landing coupling constant using the renormalization group method, and then they achieve this differential equation, which govern the behavior of that effective charge, and the result really demonstrate the Landau pole as the reference scale go to zero, the effective charge also go to zero. As you can see, then the behavior established the zero charge theorem, where QED become trivial at the short scale. It showed the fundamental limitation of the theory, and additionally, this result opens some new discussion about the need for the new theories to replace QED at high energies. Well, these slides will show you the simple derivation. One can see that the effective charge which go with the electromagnetic interaction will vanish at the short distances. Here you can see that it is just the simple integration, and it suggests that there is no meaningful interaction at that scale, and there is some fundamental inconsistency in the theory, which is the theoretical limit. Now let's see some implication in particle physics. As I mentioned, QED has some limitation. It works well at practical energy scale, but fail conceptually at high energies. This is due to the zero charge. It is the fundamental limit of the theory. However, in the quantum chromodynamic or the non-abelian gauge theories, we find some property like is avoid the problem because the landing coupling constant in QCD has the opposite sign in the denominator, previously is positive, now is negative. This property is called the asymptotic freedom. It means that the QCD coupling weakens at short distances and allow the meaningful interaction to occur instead of going to zero. See, Landau pole leads to the alternative theory like QCD to describe physics at high energies. And you can see from this graph that I plotted using LaTeX by myself. The behavior is almost the opposite. You can see that at the small scale, QCD line does not go to zero suddenly like QED. So you can see some difference. And this has a big impact in physics as Landau pole inspired the development of electroweak unification and QCD. And we see that the gate theories like non-abelian structure provide solution to QED limitations. Now, some open questions remain like how do we integrate the QED into a more fundamental framework like in quantum gravity or a grand unified theory? I think this is quite interesting to think about. Now, not only physics by content itself, but the physics as a community of physicists are also impacted by Landau pole. I mean, here, following the Landau discovery of the zero charge, there was widespread disbelief in the field theory within the Soviet theoretical physics community, and this scene was captured fully and told to us by Misha Schiffman. He also described that Landau once pronounced that the field theory was dead and it should be believed with great respect that it deserved. After that, Landau would not talk to anyone who do the research in the field theory. And this negative attitude toward the field theory remained in Landau school until 1972, even after Landau passed away. So you can see it's quite a last long impact. It lasts for like several decades and it prevents the Soviet Theoretical Physics Society to work in this field. And well, this one is not about the impact. It's just that you may see that the Landau pole and the asymptotic freedom have different signs in their denominator. Like, and this used to confuse Landau, Abrikosov, and Kalanikov once that they almost draw the opposite conclusion. This was pointed out and told by Boris Yaffe, and Landau did not do the calculation himself. He asked his students to work on it. And now, there was a letter from the Feynman written to Lev Landau to admire him about his work in superfluidity, and that the more Feynman go deeper into the problem, the more he realized Landau's greatness and intuition. And he asked in the letter for opinion from Landau about the quantum field theory. Landau replied by writing about his concern about the zero charge. You can see that, well, Landau really into this zero charge problem. And this was captured by Samyon Gerstein, who was the student of Landau himself. And well, this is a pitiful story about the Migdal and Polyakov, the same guy in the string theory, the Polyakov action. You may have heard about it. At that time, no one would talk to them about the Yang-Mills theory, and they wrote the article on the Higgs mechanism at the same time or even before Peter Higgs, and they were the student. But it was rejected by JATP, the Soviet journal at that time, for the entire 2 years. Well, they were laughed and devalued every time they try to present this thing at the seminar. So, well, this is a very regretful story about them. Thank you very much for listening and for your kind attention, and I hope you enjoyed the story. Thank you so much.